Bismillah ar-Rahman ar-Rahim. We have matrix G with NR columns and NT rows. G, K is the kth column of matrix G. So we can write down G as G1, G2, all the way to GNT. G times G transpose is equal to the sum of the outer products of the columns of G. G1, G1 Hermitian plus G2, G2 Hermitian, all the way to GNT, GNT Hermitian. We can separate GK, GK Hermitian, and then the remaining terms will be sum V from 1 to NT, V not equal to K, GV, GV Hermitian. This summation here is the matrix G minus K, G minus K Hermitian. G minus K is matrix G without its kth column. So this is G1 to GK minus 1. The column GK is eliminated, and then we have GK plus 1 to GNT. The matrix G minus K has NR rows, but the number of columns is NT minus 1. The difference between G Hermitian and G minus K Hermitian is this rank 1 matrix. In some applications, we are interested in this trace. There is an outside positive factor 1 over NR, and then we have the trace of the inverse of the matrix 1 over NT GG Hermitian plus alpha times identity. Sometimes we are interested in the same quantity, but with GG Hermitian replaced by G minus K Hermitian. As we have seen, the difference between these two matrices is a rank 1 matrix, which is GK Hermitian. We want to investigate the difference between these two quantities. One of them involving GG Hermitian. Here we are using the full matrix G, and here we have G minus K Hermitian. G minus K is G after removing its kth column. We will show that psi, which is the difference of interest, is upper bounded by NR and then this parameter alpha, which is a positive real number. This means that the difference can be made arbitrarily small by increasing NR. If we are doing an asymptotic analysis where NR gets arbitrarily large, then we can replace this quantity by that or vice versa, depending on the need. Let's show that psi is upper bounded by this quantity. Take GG Hermitian and rewrite it as G minus K Hermitian plus GK Hermitian. What we have here can be written as 1 over NT, then G minus K Hermitian plus alpha times identity. This is matrix A. Then we are left with 1 over NT GK, that's the kth column of matrix G, GK Hermitian. But I will write this as 1 over square root NT GK, then 1, which is identity matrix of size 1 by 1, and then 1 over square root NT GK Hermitian. This is matrix B, this is C, this is D. Matrix A is of size NR by NR, matrix B is of size NR by 1, C 1 by 1, and D is 1 by NR. We apply the matrix inversion lemma, which states that A plus BCD inverse is equal to A inverse minus A inverse, then B, D, and then here we have the inverse of the matrix C inverse plus A inverse between D and B. Note that in our case, A inverse is 1 over NT G minus K Hermitian plus alpha I inverse. If we apply the matrix inversion lemma, take the trace and then divide by 1 over NR, then this term will give us a term identical to this one, but with a minus sign. These two guys go away, and then what we are left with is plus 1 over NR, the trace of these terms here. After applying the matrix inversion lemma, psi is 1 over NR, the trace of A inverse, and then B, which is this column vector, and on the other side we have A inverse, and here we have D, which in our case is the Hermitian of this vector, and then between them there is the inverse of the matrix C inverse, which is just 1, plus D A inverse B, this quadratic form. Note that what we have here is just a 1 by 1 matrix, a scalar. We can write down psi as 1 over NR, and then this square root NT and square root NT can be written as NT in the denominator. This inverse is just this factor in the denominator, 1 plus 1 over NT, GK Hermitian A inverse GK. In the numerator, we have the trace of A inverse GK times GK Hermitian A inverse. If we have matrix phi of size m by n, matrix omega of size n by m, then the trace of phi omega is equal to the trace of omega phi. We can apply this result here. A inverse GK, that's a matrix of size nr by 1, GK Hermitian A inverse, that's 1 by nr, and we can swap these. and write down the trace as the trace of GK Hermitian A inverse times A inverse GK. But this is a scalar, a 1 by 1 matrix. Its trace is itself, is this scalar, which is GK Hermitian A inverse squared times GK. A inverse is alpha times identity plus 1 over nt G minus K Hermitian. This matrix here is Hermitian and positive semi-definite. We can do its eigendecomposition and write it down as Q. That's a unitary matrix of eigenvectors, lambda, a diagonal matrix of the eigenvalues of 1 over nt G minus K Hermitian. And here we put the inverse of Q. Because Q is unitary, the inverse is Q Hermitian. We do an eigendecomposition of this matrix, and we can write identity as Q Hermitian. We can take Q as a common factor on the left, Q Hermitian as a common factor on the right. Between them, there will be the diagonal matrix of eigenvalues, big lambda, and then we have alpha plus the identity matrix of size nr by nr. Then we take the inverse of this thing, Q Hermitian inverse. This is Q, lambda plus alpha I inverse. Here we have the inverse of a diagonal matrix, which is just the inverse of each element on the main diagonal. Note that all the elements on the main diagonal are strictly positive. This matrix is positive semi-definite. Its eigenvalues are non-negative. And then to each eigenvalue, we add the strictly positive real number alpha. So every element on the main diagonal of this diagonal matrix is strictly positive, and the matrix is invertible. And finally, when we take the inverse of Q, we get Q Hermitian. This is a to the minus 1. What is a to the minus 2? Take this expression here multiplied by itself. Q Hermitian, Q is identity. These two matrices are multiplied together. So we have the inverse of big lambda plus alpha I squared. And then we have Q on the left and Q Hermitian on the right. We can use this for the numerator, and we can use this in the denominator. This is what we have after taking this nt in the denominator and joining it upstairs here with vectors GK Hermitian and GK. Let this vector be C. C is a vector of size nr by 1. This is C Hermitian. This is C Hermitian, and this is C. Let's write down each quadratic form as a summation. Because the matrices in these quadratic forms are diagonal, we just have a single sum, not a double sum. The sum in the numerator is summation v from 1 to nr, magnitude cv squared. So cv is the vth element in vector c. C is c1, c2, all the way to cnr. We get magnitude cv squared because we get cv conjugate from here and cv from there. Their product is the magnitude squared of cv. And then we have the vth element on the main diagonal of this diagonal matrix. That's 1 over the square of lambda v plus alpha. Same thing in the denominator. It is just that lambda v plus alpha is not squared, because here we have minus 1 and here we have minus 2. So far, we haven't done any bounding. Epsilon, which is the difference between the traces, one of them using GG Hermitian and the other using G minus K Hermitian, is given by this expression here. Now let's do an upper bounding step. 1 over lambda v plus alpha, which is here in the numerator, write it as 1 over lambda v plus alpha times 1 over lambda v plus alpha. This is upper bounded by 1 over alpha because lambda v is non-negative, as it is an eigenvalue of a Hermitian positive semi-definite matrix. If we use this in the numerator, we get 1 over lambda v plus alpha, and 1 over alpha can be taken as an outside vector. We get here 1 over alpha nr. Then we have a non-negative quantity divided by 1 plus the same non-negative quantity. This is less than or equal to 1, which means that epsilon is upper bounded by 1 over nr alpha. We have these two traces. One of them is applied to the inverse of a matrix, and the other is applied to the inverse of another matrix. The difference between these two matrices is a rank 1 matrix given by 1 over nt GK Hermitian, GK being the kth column in matrix G. The difference is upper bounded by 1 over nr alpha. And if we are doing an asymptotic analysis in which nr is very large, we can replace this trace by that trace, or vice versa if needed, knowing that the error decays to 0 as nr tends to infinity.